Okay, I suggest we make a nice academic 5-minute late start. So for those of you who are not familiar with our CDT, there's a few visitors and we'll have more from them later. We're basically a cross-disciplinary CDT. So we do research across a whole number of fields, chemical sensing, sensing of salts, microscopy, gravitational wave detection, etc. So all of these things are sort of held together by common concepts in sensing and measurement. And the problems that you face in one area of sensing and measurement, you'll face in others. And equally, there's lots of opportunities for cross-fertilization between these. So a couple of our presentations today are on, for example, localization. I guess, Colin, you're going to talk about localization microscopy, in which case you're trying to localize single molecules. There's going to be another presentation which is on, for example, about localization of beads in tracking particles through a treasury storage. Both of those techniques are techniques which are also used by astronomers. In fact, when I've spoken to astronomers, they look down on these people and can't believe how simple their algorithms are. So really, one of the things you can do is steal other people's ideas. And in the field of precision measurement, you have some particular challenges. Particularly, everything you try and measure measures everything else at the same time. So one person's gravitational wave is another person's phase noise. So when I look at the work that Heriott and his group do on measuring gravitational waves, the interferometers that they use are very much like the sort of interferometers I've seen to measure phase noise on lasers. But you don't like phase noise on lasers, but other people want to measure it. Maybe you'll cover that, I don't know. Okay, so what we're hoping that we'll get from today's lectures is some understanding of how we can get cross-fertilization from one area of measurement, precision measurement, which help us to steal these ideas and other areas of measurement. So our first presentation today is by Harry Ward. Harry works in the Institute of Gravitational Research in Glasgow, and he's going to talk about measuring gravitational waves one day in space.
Okay. Thanks, Andy. Welcome on. So I was given the first two words of the title, but I added the byline. The role of precision measurement or precision interferometry in this business of opening a new window of the universe, the gravitational wave detection that many of you may have heard about within this last year. I think to give you a bit of background, the striking thing is that until just over a year and 2 months ago, virtually everything we knew about the universe we knew through electromagnetic observations, the kind of astronomy that you maybe will hear about in some subsequent talks. And yet, we all know from our learning of physics that essentially gravity, though it's the weakest of the forces, is the one that controls and orchestrates the universe on the largest scales, from the scales of course, our local solar system through to the scales of the galaxies and ultimately the scale of the universe itself. And though gravity does that, it has always been, at least for 100 years ago almost exactly, it had been satisfactorily described, at least as Newton did, as a mysterious force, but we knew how it behaved, but we didn't really understand what it was. And of course, it's the famous G of m over r squared. But the problem with that was, of course, that it embodied this action, instantaneous action at a distance, in its formulation, and that was profoundly unsatisfying. And a gentleman rather close to home opined round about 100 years ago that he would accept no theory of this. Is Lord Kelvin, those of you who don't recognize, would accept no theory of gravitation. So that basically he was saying that it was a mystery, and it remained a mystery until another gentleman who you will recognise had a new insight, and the new insight was to change your perception from gravity being a mysterious magical string that held two things together to gravity being a manifestation of this thing we call space-time being warped. And the idea really came about from deep thinking about whether you could have instantaneous action at a distance or whether you had to have a finite transit time. And once you embodied that in what he called relativity, it naturally fell out that gravity was a manifestation of warped space-time. He was a modest chap, as you can see this. I had to put this in just because it might remind you of some local location. This was Einstein at Glasgow University, just up the hill there, receiving his honorary degree. And I always like that quote where he says that in his address, not that I have an unduly high opinion of the importance of my own endeavours, which is an interesting lesson in scientific modesty. Anyway, mathematically, gravitational waves are just the solutions of Einstein's field equations. That's all they are. But in physical terms, the best description, I think, came from John Wheeler, where he said that the right view to have of gravity is that matter tells space how to curve, and the curvature of matter tells space how to move. So if you think of us and the Earth going around the Sun, it's not by magic, it's just the local space has been distorted by the presence of the Sun. You can picture it in this rather poor 2D analog of a sheet that's been distorted by the presence of a heavy object, and then the other object, in our case the Earth, tries to go as straight as it can, but it's going in a curved space, and so it executes an orbit. And so that's the picture that you should have of gravity. And gravitational waves then are just perturbations in that curvature. So if we had the misfortune to have the Sun to bifurcate into two, you can see that that would cause distortions of the space-time to ripple outwards, and eventually they would come to us, and we would know about them. That's the good news. I said at the start that gravity orchestrates the entire universe. It would be very attractive to be able to see its orchestration, to see its music, and that's the target when we talk about trying to detect gravitational waves. We want to look at these ripples in the curvature of space-time. And the killer is that, and this is where precision measurement comes in, the killer is that gravity is, of course, a weak force, and these distortions, which are characterized in terms of the dimension of strain they produce in space, if you want to sense them here on Earth from typical astronomical sources, you've got to be able to sense a strain. This is a change in length divided by the length over which you make the measurement. The convention is called H in our business. You want to measure strains there that are fantastically small. Perhaps, to begin to do astronomy, you're talking about parts in 10 to the 21. So in terms of your physical size, it's you changing by about 10 to the minus 21 of a meter as a gravity wave goes by. And if you think of the distortion produced, it turns out to be a quadrupolar distortion. And if you have a gravity wave propagating into the plane of the board and you're a sinusoidal gravity wave, then what you would do is cause a ring of test particles, depending on your polarization state, a ring of test particles to become oblate and then back to a ring at the midpoint of your cycle and then squashed in the opposite direction. So you're alternately compressing and elongating as the gravity wave propagates through you. And that gives you a hint of how you might, if you were daring enough to think that 10 to the minus 21 were doable, how you might detect them. Because if you, again, think of the gravity wave propagating into the plane of the diagram there, and you set yourself up with a microscope, then all you have to do, all in inverted commas, is to wait and see the gravity wave compress one arm at the time as it extends the other. And that's the beginnings of how you could make these ultra-sensitive measurements. If you want to measure a change in length of a part in 10 to the 21, then you need a reference that is at least as good as that. And there isn't that available. There aren't lasers stable enough that could do that. But if the gravity wave is going to helpfully provide you with a differential motion between two lengths, then in principle, you set up two arms, and the gravity wave is the thing that causes the differential length change. But then there's a challenge, because it's clearly a very small number, and you've got to decide what length of arms to choose. And there's a whole range of issues that come in, and I don't pretend that I've included them all here, but the strain in space that gravity wave produces is small, so it's going to be hard to measure. There's no doubt about that. And so you want to make the arms long, because remember, H was delta L upon L, so if you're having trouble measuring delta L, you better make L big so it gears it up. But there's a limit, and at least on Earth there's a very obvious limit, which is that the length, well, the Earth's curved, that's one thing, but even worse than that, you want your laser beams to propagate in vacuum, otherwise the fluctuations in refractive index in the air would be a huge swamping signal. So you have to have a vacuum system, so it's clearly going to cost money. And so that's a limit. But there's actually another limit, which is that if your gravity waves that you're trying to detect are dynamically changing, they have characteristic frequencies. And so if you spend too long in having a light beam propagate along the arm and back again, then perhaps the sign of the effect of the gravity wave will have reversed, and then you'll be sunk that way. So there's a kind of natural length scale for the arms, depending on the frequency of the gravity wave you're trying to detect. One trick you can try to play is, and you maybe see this done in other branches of precision measurement, is that you could make your arm appear to be longer, in other words, get the light stored for longer if you reflect it backwards and forwards many times. And there are various strategies for doing that. You can have discrete reflections, or like in spectroscopy, you can have a resonant cavity where you store the light for longer to maximize the interaction time with the gravity wave. And all of that is potentially possible. The storage issue is certainly one that has transformed the gravity wave business maybe around about 30 years ago with the first generation of ultra-low loss mirrors. And certainly the situation today with the advanced LIGO detectors would not exist were it not for these very low loss coatings that are now available, originally developed for laser gyros, I believe. So all of that is potentially allowing you to get high sensitivity. But you can't have the arms too long. And so when you think about the implications of all that and put it all together, the other constraint you have is that the requirement to measure these gravity waves is to make measurements between mirrors that are essentially free. You would like, the Einsteinian description of them is that these are inertially pure, doing their inertial thing, test points, and you measure between them. Because what the gravity wave does is change what's called the proper distance between inertially free particles. That's the proper distance as the technical term for the distance measured by light. On Earth, you can't have mirrors that are free because they'll fall. You let them go, they fall to the ground. So the best you can do is to have them free at the frequencies at which you're trying to detect gravity waves. And the simplest way to do that is to hang them as pendulums, because then, okay, they're maybe not free down at DC or very low frequencies, but certainly once you get well above the pendulum resonance, they act as though they're free. If you're prepared to go into space, then it's easier to get them free, or at least you might think it is. Turns out that that's not so easy either, but at least in principle they'll float around without the 1G environment of the Earth. So you've got to hold that into your thinking. And the other issue is that as soon as you begin to assemble any physical structure, you will have, inevitably, unless it's absolute zero, you will have internal thermal noise, and that produces some jiggling of, in the case of the mirrors, the surfaces of the mirrors, or even worse, the surfaces of layers of the coatings on the mirrors, or in the case of pendulums, the actual pendulum will vibrate thermally. And so you need to control that, and one way is to make sure that all of these resonant features are very narrow, because then their thermal energy is confined to a very small part of the frequency spectrum, and other parts, the parts where you might hope to be making measurements, are relatively clean. So there's a whole range of issues that have to factor in once you start to dig down into these very low noise levels. And just to give you an idea of the complexity that's involved, this is a pendulum, but you can see it's far from looking simple. This is one of the ones that was developed in Glasgow for the advanced LIGO detector. This is the mirror that's from that point to many kilometers away is where you're making your measurements, but you can see it's actually a complicated structure of multiple pendulums. And that's because you also on Earth have to face the contaminating effect of seismic vibrations, and pendulums, or at least multiple stages of pendulums, are a good way to insulate yourselves from that. If the world moves at the top of a pendulum, the bottom doesn't move very much, and so that provides isolation. So the end result of all the thinking and optimization is that, at least for current generation ground-based detectors, thousands of meters was about the right scale. So in LIGO with 4 kilometers, for example. If you're think about what that implies about your measurement precision, you're going to have to measure something, and I apologize for being spectral densities, but it's the way we think. You've got to be something of the order of 10 to minus 19 or 10 to minus 20 meters per root hertz in the region in which you're trying to detect, and that for LIGO is in the tens to many hundreds of hertz region in the spectrum. If you're prepared to go into space, then things change, and just as you may hear from other speakers, the electromagnetic spectrum is covered not by one telescope, but by a whole range of different kinds of telescopes optimized in different bands. Just as for gravity waves, there are a whole band of interest that for different signals populating different parts of the band. Very big things typically emit gravity waves at very low frequencies, maybe millihertz or below, whereas small things like the size of the sun emit signals if they explode more in the hundreds to kilohertz region. So it's not one detector fits all. If you go into space, you've got the scope to optimize things differently, and so you can have arm lengths that are huge because you don't need to pay for the vacuum system essentially. And once you make that leap of thinking that in space you can have separated mirrors, essentially separated spacecraft, then you're at liberty to make the arms extremely long. And the current designs for the first detector, which we hope to fly, I think called LISA, call for arm lengths of a few billion meters long. And you only then, to get the sensitivity that we require, you only then have to measure picometers over billions of meters. Now that sounds scary, and it depends on your perspective whether you find the 10 to the minus 20 meters per hertz on ground scarier than the picometer in space over billions of meters. But it's still the same, approximately same strain sensitivity. It's just the technical challenges are slightly different. But actually, the technical challenges have a lot in common, apart from the fact they're both challenging. They have different demands on the techniques used. One that you have to deal with first and foremost is that you're measuring dynamic signals, and so you've got to make repeated measurements to be able to resolve the waveform that the gravity wave is giving you. And so if you're trying to measure things that are evolving quickly, you need to sample quickly, and so your interval over which you make a measurement is short, and that corresponds to needing lots of photons. If your photon shock noise is not going to be a limiting factor, so you perhaps need big lasers or lots of laser power stored somehow in your optical system. And that's an issue for LIGO, where they perhaps put in 50 or 100 watts of laser power and then multiply it up inside by a fabric-barrel cavity system. Once you get up to the many tens of kilowatts region in stored power, and it has to transmit through optics, then you get serious thermal issues, and that's one of the big problems for the ground. The problem in space is not the same, at least not quite the same. We're not ever at the power levels where thermal effects matter, but on the other hand, it's hard to get laser power in space. And it's hard to get power in space, period, but it's hard to get stable laser power in space. The best we can do at the moment is of order watts transmitted in a stable sense for many years. So we're fortunately in space we're looking at slower signals, so we don't need so much power, but it's still a challenge to get it in the space environment. There are lots of other issues. I won't go through them all, but one biggie is the business about laser frequency fluctuations. That if you have an interferometer and that pictorial diagram I showed about Michelson looks all nice, that it would only be sensitive to differential arm length changes, but if your arms aren't the same physical length in terms of the optical path, then of course if the laser frequency changes, that looks just the same in terms of its effect on the output, the phase of the output interference pattern. It just looks the same as a change in differential arm length. So laser frequency noise is bad. In the ground, you control it by many stages of stabilization. In space, we have to do something similar using the long length of one of the arms as a reference. So the big success of the year, of course, was the first detection that happened in mid-September 2015. It was announced in February 2016, and that's the one that took the world by storm, if you like. I mean, it is an astonishing thing. It was astonishing to us that actually almost the first time it was turned on in its newly reconfigured state with new sensitivity that nature presented us with the signal, actually even before it was officially turned on. And all the more striking when you think of it that the signal originated when I think on Earth there was probably not even multicellular life. It was 1.3 billion years ago that the signal happened, and it's been traveling to us ever since. And it was, as many of you will know, it was dramatically new physics as well, because it was the first observation of a binary black hole system, two extremely massive 36 and 29 solar mass black holes ending their in-spiral. They spent most of their lives very happily orbiting each other, emitting gravitational waves as they did, of course, carrying energy away from the system, and so their orbit decayed in the in-spiral together. And it was a truly cataclysmic event. In the time scale of just a fraction of a second, something like 3 times the mass of the sun was converted into pure gravitational energy. And we were left, that's a chirp. Maybe can't quite get it, but that whoop sound, it's slightly shifted in frequency to make it audible, but you can see it in the frequency time diagram there. That was the twin two different detectors in LIGO, one on one side of the US and one on the other side, almost coincidentally detecting the chirp from this event. And it was a thing that had been postulated, of course, but nobody had ever directly seen evidence for a binary black hole system like this. And here we're seeing it not through some, big electromagnetic signature, but we're seeing genuinely the gravitational effect as those two black holes coalesce into one. Anyway, the point of telling you about that was to motivate this diagram, which shows a thing very typical when we're making these precision measurements, that this is a plot of the expected sensitivity for a thing like advanced LIGO. But the thing to focus on is the fact that there's lots of colors. The black line is the sensitivity that we could achieve in an interferometer if we cope with all of these other lines, myriads of sources of noise, that all conspire to limit what we can do in different parts of the spectrum. And that's typical when you make precision measurements, when you're beating into new areas, that you essentially face an onion of problems, that it's many layers, and you can remove one noise source, but there'll be another one there to catch you. And essentially it's peeling back those onion layers that have taken us probably the 40 years that the interferometry business has been going to get to this point for gravity waves. But if we want to do something equivalent in space, we face many of the same challenges, but not quite identical ones. We can, as I mentioned, have big long arms, that's easy. And the current designs for space-based detectors call for 3 spacecraft. In each of them, there are telescopes emitting beams of light to opposing spacecraft. It's handy to make them in a triangular format. And the issue is that you can send laser light from one end to the other, but it's an awfully long way, and you have inevitable diffraction. And so, with any reasonably sized telescope, maybe of that scale, in a typical spacecraft, your diffraction is still non-negligible. And if you emit laser light from a telescope of that size, once you're a few billion meters away, it's tens of kilometers wide. So you only intercept a tiny fraction of the light. It's not like sending a laser pointer to the end of the room and then getting the light back again from a mirror. You only intercept a fraction, and if you reflected that back, your fraction times a fraction would be nothing when it came back, and so you would leave very little light. So in fact, we use laser transponders. I'm going to zip forward to something because I wanted to show you something about how we are approaching that in space. The challenge in space is to have the mirrors free. And just as on the ground we did it with pendulums in space, you would think they would float. Nobody quite believed they would. And it's partly because space is a very noisy environment. You would think that was anomalous, but in fact, in our local space, the sun, the radiation pressure from the sun is a very non-stable thing. And if you just put a mirror sitting in space and allowed sunlight to shine on it, you would have a DC force, of course, but you might be able to ignore that if you're just searching for dynamic gravity waves. But the sun's output fluctuates, and so the force is actually dynamic. And so the whole the masses would vibrate around in a factor of 1,000 or 10,000 times bigger than we could ever allow. And so we always knew we would have to put mirrors, these cubes, in a secure environment inside the spacecraft, with the spacecraft acting as a kind of shepherd round about them. And that needed to be done for LISA by a factor of about 1,000 times better than had ever been done before in space. And nobody believed that was credible. So we had to create this mission called LISA Pathfinder, which is the other great gravitational success of 2016. We put 2 of these, essentially compressing one arm of a big space detector into one small spacecraft. We then measured the separation between them. Instead of billions of meters, it's only tens of centimeters. And we built an interferometer here in Glasgow, the thing in the middle there, which measured with a resolution of picometers that separation. And then it was a particular kind of interferometer called a heterodyne, where essentially you're using 2 colors of light and you're making a beat note between them. And as the masses move, you change the phase of the beat note, and you measure that. And the complexity is you have to do many things. And I'll show you the picture of what we made. We made you can hardly see it, but it's a thing that's about 50 centimeters square there. You get the scale from the fingers, probably Christian's fingers. Then to do that, we had to develop ways in which to make things that were ultra stable, because when you're trying to make measurements down at fractions of a hertz, It's things, you can't allow them to vibrate. Certainly, if you're launching into space, that would break. And so we developed new techniques for bonding things together with very high precision. And then the good news is that the scary point was that our interferometer was at the very heart of this measurement in the spacecraft. This is an exploded view with two group masses and our interferometer, and then you package it all together and send it off. And that's the moment where you hold your breath because it's a hellish environment to experience. I promise you to know your decade of work is about to explode in what looked for all the world like an explosion, but in fact was a successful launch. And then, cutting to the chase, the end point was a very successful mission located about 1 billion kilometers away from Earth. It's called the first Lagrange point. And I'll just show you the answer. And the answer is that, first of all, the interferometer performed better than we could ever have imagined. The test masses floating freely, lined up to give us contrasts better than 99% of the interferometers. We measured the noise on the first day, and it was quieter than we needed to do for the entire mission. This is measured in terms of the residual acceleration, differential acceleration of the group masses. Our target was this dotted line. We were already down there. We tweaked it up, and the targets there for the mission and for the real mission that we want to fly in 2034, the LISA mission, that's where we got to almost immediately. With a bit of effort, that's what we got to. We now know the residual limitations, interferometer noise, much better than we ever needed. Residual gas molecules hitting the group masses, handleable. Bit of extra stuff at low frequency, we now understand it. And the thing is that we're now down essentially at the LISA requirement, orders of magnitude better than we set out to do. And so we created, in that mission, we created essentially, that's the interferometer, well below our requirements. We created essentially the quietest space probably certainly in the local universe, shall we say. Orders of magnitude better than these earlier missions have ever achieved in terms of accelerometry. So that's the 2016 has certainly been the year when gravity waves came to the fore, but certainly when astronomy began. I think the ground-based detections are underway again, and you can confidently expect further detections there. Pathfinder was an astonishing success. Actually, we were all quite taken aback. When you see noise as good as that out of the box, you begin to wonder, but in fact it's true. And the proposal for the LISA mission, which we hope to fly in 34, is due in just over a month. And it's a tale of great persistence. I mean, some of us have gone slightly grey in the process, but it's 40 years of quite exciting work in precision measurement that now is certainly producing its results. Thank you.
Thanks very much, Harry, for a fascinating talk. I would love to be in that position of getting a tenfold better result than I did. For me, it often goes the other way. We have some questions for Harry.
Hello. I was just wondering, in LISA, you have the different parts of the interferometer will be much farther apart.
Yeah.
So would that be a difficult thing to ensure that they face the right direction?
Yes.
Or is it easy?
It's both difficult and easy. It's difficult if you try to do it by dead reckoning, but we are sending the brightest star from one spacecraft to the opposing one because we're sending a beam of laser light. And so what you require is that the laser light coming at you and the laser light you're going to send back are essentially collinear. Maybe not quite, but essentially collinear. And the laser light provides its own reference there because you can interfere the two beams, and you can detect that interference not just in an integrated sense, but in a spatially sensitive way. You can detect them in quadrant detectors, and so you can look at the angles between the incoming beams, and that acts as your signal to drive your pointing of your spacecraft. So rather than just doing it by conventionally spacecraft are pointed by looking at star maps, we've now got the best star map you could ever imagine because we've created a bright star in the distance.
Have time to ask one more question? One thing I've often wondered strategically, if you'd been Einstein sitting there 90 years ago, whatever it was, would you have come up with all these problems that you showed you know your sources.
Mm-hmm.
One would never necessarily guess that the thermal noise in the coatings was the major issue.
Yeah.
Would you have ever done it if you saw this problem?
If you want the honest truth, I don't think 40 years ago we had concepts of things like thermal noise in coatings. And that's been one of the things that has crept up on us over the last decade. I mean, I think other things Einstein would have understood. He would certainly have understood about gas, the effects of propagating through finite pressure. He would have understood. Well, he had the beginnings of understanding about lasers, of course, so he might have almost understood short noise without understanding that he understood it. So, yeah, I think for many people, even when I was starting out, many people just thought this was a ridiculous thing to attempt. In fact, I was told by very erudite physicists that it was a ridiculous thing to attempt. I was wasting my life because it was obvious that you would never be able to measure things as small as this. But nothing's obvious, you know. We didn't stress it, but in the ground-based detectors, the thing that is looming is the quantum limit. And we've already, created some experiments to artificially demonstrate that. But that is a potential limitation, but actually not a real one, because there are schemes that, depending what you call them, whether you call them quantum without definition or actually dating, there are schemes to avoid the quantum limit there too. So there's no real limit immediately in sight.
Okay, thanks very much. Our next presentation is sticking with astronomy. It's been given by Colin Cunningham from the Astronomy Technology Centre at the Royal Observatory in Edinburgh. He's going to be talking about precision measurement in astronomy. And Colin has a title which showed me he made of himself, which is technology champion, but he couldn't quite tell me whether champion was a verb or an adjective in my case. I'll let him decide.
Yeah, that's a good question. I think it's supposed to be a verb. But anyway, so I'm going to be talking about precision measurement in astronomy, and I guess I should have called it precision measurement in electromagnetic astronomy following the last talk. Perhaps this is old-fashioned stuff now, after last year or this year. Anyway, so you can argue probably that all of astronomy is precision measurement, so I'm going to start right at the beginning. Okay, I can't see what's going on with this one. So this is titled Brahe, end of the 16th century. He was looking at measuring the position of stars using his eye and some complicated mechanical devices that he set up in an island off the coast of Denmark. And he was able to get a precision of 1/10 to the 4, which is actually pretty amazing, considering he was just using his eye and these bits of brass. So that's 10 arc seconds in 180 degrees across the sky. Since then, we've gone a long way, but of course those measurements were the thing that allowed Kepler to start to understand the motions of the planets and to formulate his laws of planetary motion. And of course, going back to Newton that we just saw, that's what enabled Newton to set up his laws of gravity. So all down to measurement. Since then, of course, we've come a long way with the invention of the telescope, of course, and taking it to its extremes of the ESO's very large telescopes. In Chile, 480-meter telescopes connected to smaller telescopes to make an interferometer, and the precision here is 1 part in 10 to the 7, so it's 1 milliarc second in 180 degrees. So that sounds like huge progress in those 400 years. But recently, ESA has very successfully had the Gaia mission, which is a precision astronometry mission, in other words, measuring positions of stars. And it does this by having 2 telescopes mounted on one optical bench and measuring, if you saw that quickly, anyway, you can see from this, it's looking at star positions at 2 positions in the sky and then scanning around the sky to get a complete measurement of what can be seen within the measurement limits. And this allows you to get a complete map of our galaxy. So the sun's at this end of the galaxy, and you can start to measure the position of 1,000 billion objects in our galaxy, which is actually there are 100 billion, so it's only 1% of the stars in our galaxy. It's still a huge number, and they're measured to extreme precision. what is it? What's the number I gave earlier? There you are. So it's I'll move around here so I can see what I'm doing. Okay, so the precision here is 10 microarc seconds, which is equivalent to a human hair 1,000 kilometers or 2 centimeters on the moon. And this is a billion stars, as it says here, 1% of the Milky Way stars. Most of the talk I'm going to discuss engineering challenges on the ground, though. So building a telescope on the ground is even more difficult than in space in many ways. If you look at this chart, this simple picture here, it shows some of the interfering noise sources in the measurement of any position or spectrum or whatever you're doing with a telescope. If you look at the detector, there's the detector noise, and there's cosmic rays getting onto it. There's also thermal emission from the optics, which is important in the infrared. And then you've got stray light from the moon and all sorts of other things. But outside as well, outside our atmosphere, we've got all these other sources, atmospheric emission with galaxy lights, lights. And of course we've got atmospheric turbulence. But on the ground, the other big perturbation is the telescope moves around. So as it moves around, the telescope structure moves, and this gives you potentially flexural changes. So stability, the stability against wind, changes in temperature, are all going to affect the precision of your measurements. So I'm going to explain some of these, how we get over this with some examples, starting with the European Extremely Large Telescope, which was my previous day job, was to be the UK director for this big European project. This is to build the world's biggest optical infrared telescope, 39 meters in diameter. You can see from the scale of the vehicles, that's pretty huge, and it's in the Atacama Desert in Chile, and it started being built now. The key part of it, of course, is the primary mirror. So this is, you can't make a mirror in one piece of glass at this size. So it's made with 798 segments, each about this big, each hexagonal in shape. The form accuracy of these is something like 30 nanometers RMS, so you've obviously got a measurement problem there in actually measuring the accuracy of that shape. And then you've got a very smooth surface needed, less than 3 nanometers micron roughness. So these are very precise objects, and you need a lot of them. This is an example of some of the prototypes. So getting back to the flexural problem, as the telescope structure moves around the sky, the steel structure moves by a couple of millimeters. We've got to keep these accurately positioned to something like 10 nanometers. So they're supported on a 27-point whiffle tree structure with actuators to push them into place as the telescope structure changes, and as thermal changes occur as well. And this is all controlled by edge detectors so edge sensors. So we're back to sensors again. These sensors that we use are actually electromagnetic sensors, so they're an induction coupled between an emitter and a receiver, and you measure the Friedman and the tip tilt, and also the dihedral, and use this to correct the position of the mirrors in real time. This is a big problem. You've got 4,630 of these, huge number of controllers and electronics. So it's a huge control problem as well. The mirrors themselves are manufactured using glass ceramic. We need 931 of them because we need spares. We have to recoat them, one of these every day, just about. So we need a full set of spares as well. They're made by high precision grinding, polishing, pre-polishing, and then cutting into the hexagonal shapes, and then iron figuring to get this very final shape. And in fact, at the end of it, there's still a very small amount of bend that's putting onto the mirrors to correct the final errors. The critical part of this, of course, is the measurement. This is an example of a measurement tower and a polishing setup from the Optic Lindell setup in North Wales, which was used to produce some of the prototypes. And the reason for having the big tower is that the radius of curvature is 49 meters or something. Well, if you look at them, they look almost flat. So measuring to that 10 nanometers is pretty tricky. The way it's done is to use a piezo interferometer and a spherical test reference. Now that will be fine if the mirror was spherical, which it isn't in this case. So we've got to put in some correction to allow for the change of shape of the waveform that we need to put onto this aspherical surface, and that's done with a computer-generated hologram, CGH. That sounds reasonably straightforward. It ends up with a much more compact interferometer than we have if we didn't have that system. Unfortunately, there are 133 different shapes of mirrors in the system, so we also need 133 CGHs. A non-trivial measurement problem. Right, the other thing that causes perturbation on the ground, of course, is the atmosphere. So if we look at this image of the moon, should have a moon, yes. So if we look at this through any telescope on the ground, we see, if you look closely enough, you'll see fluctuations. If you go into space, you'll get a perfect image. And this is purely because of the atmospheric distortion caused by the layers of the atmosphere which change the refractive index of the atmosphere. If we look at a point source, we get this sort of horrible thing, which is shaking out all over the place, and the twinkling of the star, you could call it. And what we'd like to do is to correct that, so that we go from this horrible thing to something like that, which is much more like an airy disk, in other words, a fractional image. If we don't do that, the limitation on the ground will be something like 500 milliarc seconds. With a 40-meter telescope, the diffraction limit is more like 4 milliarc seconds. And so to do that, you've got to use something called adaptive optics, which is also based on precision metrology, precision measurements. This is the wavefront that's coming through the atmosphere, distorted by the atmosphere. It would be playing parallel if it was coming from a point source and we were in space, but it's not. But what we do is we put that onto a deformable mirror, which is exactly the opposite shape to that, and it ends up with corrected wavefronts which are plane, and you get a diffraction image. And this is done with a system of using a wavefront sensor. So you've got to measure that precisely, and then put in a correction for a real-time computer to change the shape of the mirror. So we're back to precision measurement again in astronomy. The way to do that is using a wavefront sensor. There are two main types. This is a Schack-Hartmann sensor, which is basically an array of microlenses which deflect the light onto different parts of the CCD chip, and you can, by measuring the deflection, you can reconstruct the shape of the waveform, which is nice. You need a very fast low noise detector, which is where the challenge comes in generally. Another scheme which is often used as well is to use a pyramid, which is basically a glass pyramid with a very sharp point, and this deflects the light, so you get 4 images, and you measure the movement of those, or change of intensity of those 4 images, and that also allows you to reconstruct the wavefronts. So they're the different protocols, but they're both very much dependent on the detectors, which are really state-of-the-art. For an extremely large telescope, we need large detector arrays, which are almost zero noise, and they have to work at about 1 kilohertz. So that's just about at the state-of-the-art of CCDs. Okay, the other aspect of precision measurement for us is, this is our business in Edinburgh, building large cryogenic instruments generally for use in the infrared or thermal infrared, up to 28 microns from the visible, and also into the submillimeter or the terahertz range. This is a submillimeter camera or SUDA2. Both of these provide challenges in the operating environment for the optics and the mechanics within there, because we have to cool them to low temperatures. In this case, to about 6 degrees Kelvin, and in this case, to less than 100 millikelvin. So we've got significant problems in just doing the cryogenics, but also most of these instruments need to have mechanisms in them as well. So these might be typically a wheel that holds filters. This is from a space mission, actually, the James Webb Space Type Telescope infrared instrument. And this is quite an old image of a general purpose spectrograph, but it's good. You can see it's got lots of mechanisms for turning the wheels, focusing and translating the detector, and so on. All of these have to work in vacuum at low temperature, and that has its significant problems. A lot of these are to do with metrology and measuring position. The problems are often to do with thermal mismatch, so we have to be very careful what materials we use. Vacuum compatibility, we've got mechanisms in here, but we can't have any liquid lubricants, so we have to use dry lubricants. And you have to be very careful that you get the design right, because thermal contraction can cause excess friction in those bearings. That can make it worse. And of course, we need high reliability. Operating these instruments on the top of the mountain in Chile or in Hawaii or somewhere is very expensive business, at least 10,000 euros a night. So we don't really want to be switching our telescope off because a position sensor is broken. So we have to have extreme reliability, and we need repeatability for these mechanisms. Often it's not actually, we don't need accuracy, you just need to be able to go back to the same position. We don't actually care where that position is because we're using calibration schemes on measuring objects in the sky. It's precision that we want. And the way we've done it over maybe 20 or 30 years, we've evolved a sort of standard mechanism and position sensing philosophy, which is kind of simple. We use an aluminium wheel with a Vespel plastic worm with dry lubrication, and a stepper motor which is kept cold at the same temperature as the rest of it, so we don't have long jacks going outside the cryostat. And we measure the position using a simple microswitch. So we go against the data, detect the switch changing, then move back slowly using the stepper motor until the switch switches back on again, and that gives you your data. And then you go to positioning by using the stepper motor and counting steps, which is fine, but there's always a slight worry that you might have lost steps somewhere if you've got excess friction. So what we'd really like is to have a resolver, a radio frequency resolver, as you might use in a room temperature precision rotating mechanism. Unfortunately, they don't tend to work at low temperatures. We've been doing a research program for a couple of years to try and validate a type of resolver at low temperatures. So far, we've got down to 150 Kelvin, so we've got a way to go. And a lot of the problem, of course, is because of the electronics involved, which work at temperatures. So working with manufacturers to get a resolver, a position sensor that will allow us to do this measurement in real time rather than counting steps back on the data. Okay. The other thing we want to do in astronomy generally is to not just look at one object at a time, and we don't just want to do imaging, we want to do spectroscopy. And this is called multi-object spectroscopy, so where we can take a field and measure 20, 30, maybe 1,000 different objects, look at their shape. There may be distant galaxies in the early universe, look at their shape, look at the spectrum at each of the positions, something that's called integral field spectroscopy. So we'll get a data cube for each of these objects, and then data reconfigure this so we can do one observation and then another one. Of course, this gives us much more efficient use of this very expensive telescope time, because we can do a whole survey in a matter of days rather than do one object at a time, which could take years. So this is very efficient and a very popular way of doing astronomy. It becomes more difficult in the infrared because we've got the same problem of cryogenic mechanisms and position sensing. So this is an instrument we built a couple of years ago on one of the BLT telescopes. It's called KMOS. This is the nascent platform of the telescope 8 meters across. So this is a big instrument. We just managed to get through the gate of our observatory. So it's probably the biggest instrument we've built so far. We're dwarfed by the instrument that we've built, but extremely large telescope. It uses sort of robotic arms, effectively, which position a pick-off mirror into the field, so they move that way and go that way. And we've got 24 of these to enable us to get 24 objects at a time. Operate at cryogenic temperatures, so we've got the same problems with the mechanisms, with the friction and the lubrication. But we have to keep the position of this mirror steady to something like 15 microns as the telescope, as the instrument rotates to the object around the sky. So there's significant problems with that, which have been solved. We've got 24 pick-off arms. When you look at the mechanism, it starts to become quite complicated. And obviously there's a whole set of measurements we need to do to make sure we're in the right position of all the instruments. So we have a metrology system that measures the position. But actually all the positioning is done by the same mechanism of using drives and microswitches. So it's kind of simple, but it works. Right, the next generation instrument that we're building for this BLT is something called Moons, which is perhaps even more of a challenge for us. As you can see, it's going to be even bigger. It's actually 3 spectrographs that are fiber fed, and they're fed by 1,000 fibers. Each of these fibers is held on a positioner with 2 axes in it, so that you can rotate the fibers held here, and you can rotate them and position the 1,000 fibers anywhere in the field. And this is what happens when you put these mechanisms together. The mechanisms are about that much in diameter, and they incorporate a very tiny stepper motor in this case, made in Switzerland. About 2 stepper motors for the 2 axes, and as you can see, they position in places just by rotation. One of the challenges, of course, is that you probably noticed that you could actually make these crash into each other. Just be much careful. We've got some clever software to stop that happening. Is that working? Oh, yes. So that's what it looks like when you've got 1,000 of these. So that's great. And if we could rely on the positioning using the stepper motors, we'd probably be very optimistic. So not only do we need some means to stop, make sure that they don't collide, if they do collide, that we can recover. We actually measure the electrical resistance if we match it. And if we get short, we know the touch, so we can recover our position. So all we need is a metrology system, something that measures the position of these fibers. This is actually being developed by colleagues in Chile, and it's a system using a set of cameras and illuminators which illuminate the whole focal plane. The focal plane is about this big with these 1,000 fibers on it, and we need to measure the position of the fibers to something like a tenth of a pixel. So it's sub-micron measurement of all these fibers all simultaneously. And what we do is, if you look at the positioner, the fibers here, and we've got a pattern of dots which we fill in with paint. They are filled with white paint, and you then measure the position of these dots using a centroiding algorithm, which is actually the same sort of centroiding algorithm we use on the Gaia metrology mission in space, astrometry mission in space. So we can do this to fractions of a pixel, and we can use this to get a map of where all the fibers are, so that we know what the areas are, and we can calibrate this probably at the beginning and the end of the evening, of the night's observing, and then from that point on we know exactly where all the fibers are going to be as we try to scatter. But again, that's a precision metrology question. Right, the other bit of precision metrology in astronomy is to do with spectroscopy. And one of the major successes over the last 20 years has been the discovery of something like 1,000 planets, or 3,000 planets, most of them by the radial velocity method, by looking at the Doppler shift of the light from the star as it wobbles. It's wobbled by the planet going around it. You can see the Doppler shift in this animation, so the spectral lines moving around. And so using that, you can look at the light curves, and you can work out from the light curves what the mass of the planets are. In this case, this Gliese 581, snappily named star is shown to have 3 planets going around it. And to calibrate this, you want to use something like a frequency code. This is work that's been done in Glasgow, Heriott University, sorry, Edinburgh, Heriott University by Derek Reed's group, using a train of femtosecond light bulbs, which in the frequency domain give you a code of very precisely controlled spikes, which can be tracked back to an atomic clock, so they're very, very accurate, and it gives you the capability to measure the spectral lines very accurately. This is being done by Derek's group on the SALT telescope in South Africa. So it proves its work. Now, I've got one final thing to show you, which it should be managed 1 minute, I think. So going back to the big telescopes on the ground, this was the original plan for what was called the overwhelmingly large telescope, which was 100 meters in diameter, which turned out to be too overwhelmingly large to be done for the money we had available. But actually the idea was quite interesting because this is actually a spherical mirror, so each of these mirror segments is identical. So we were thinking, what could you do in space with this? So formation flying, we've heard about with Lisa, and one of the concepts for an X-ray mission was with formation flying with two satellites. So could we use this to make a telescope? So this is the idea. You somehow build a 100-meter mirror in space using spherical mirrors with a separate secondary mirror on a separate spacecraft, and you build your mirror by some mythical additive manufacturing process, where you rotate this robot around and gradually over time you build up this spherical mirror. I can tell you how we might do that offline if you want. And this kind of looks completely mad, but actually we've done that optical design, shows it works. If you have a 100-meter mirror and you have your secondary mirror about a kilometre away, you can get diffraction limited performance on very narrow field of view, which is what we need to do direct imaging of an exoplanet like the Earth. If you look at the secondary mirror, it's actually not too big, 4 meters in diameter, and it has a corrector here which gives you the diffraction performance, and these are quite simple lenses. So it's kind of feasible on paper, and actually the stability you need for the position accuracy is 1/4 of a millimeter over a kilometer distance, which sounds quite hard, but actually is quite close to what's going to be state of the art in a couple of years' time when the Kroger 3 mission is launched by ESA. This is 2 satellites being used for doing coronagraphy of the sun, and the accuracy they can do should be about 3 times worse than we need. So we think in the time scale that you've got to develop additive manufacturing in space, which is probably 50 years, we should be able to do it. So these are the challenges I feel for precision measurement in astronomy. Waveform sensing, and the challenge is usually going to be the detectors. Metrology of highly aspheric mirrors, still not straightforward. Position sensing, more mundane, but position sensing within cryostats is still important and tricky for us. Calibration of high resolution spectrometers to enable us to understand more and more exoplanets, and then possibly the measurement of free-flying structures in space.
Colin, we have some questions. Don't be shy.
Is there a role for optical measurement in cryogenics?
Yes, I think there is. We generally shied away from it because we don't really like having optical measurements going on anywhere near our detector. It's very sensitive, difficult to switch it off. But probably not for real time, but for actually measuring the position of mirrors relative to one another. Yes. So far, we're not nearly needed to do it, but we think we will with future instruments.
More questions?
Your additive manufacturing in space, what would the mass of this be? What are the biggest problems with additive manufacturing in space?
You've got to start working out the mass. The idea is you use a mantle and spot a code onto the mantle to get the fine surface, and then you build up the structure behind it. So in principle, you can make it pretty light because basically the idea is you're launching material into space rather than structures. So you don't have to make them stiff enough to stand up to launch like we saw. That's the idea. So in principle, it could be relatively low mass. On the other hand, you still have to make sure the resonant frequencies are low enough for that thing to work. But on top, if it does work, you can then use the adaptive optic effect to verify it does work. All there. But perhaps not yet.
One of the things that's very striking about your presentation, lots of disciplines, a lot of mechanical engineering, electronic engineering, software. How many people who work in this sort of field actually interested in astronomy, and how many are actually really interested in the instruments? What gets them out of bed in the morning?
Different sorts of people. I mean,
we need everything.
Yes, I mean, I think we try very hard to make sure that we don't do things for their own sake, in other words, just because they're interesting engineering problems. But we do make sure all our projects are completely science-driven. That whatever we're doing is, so the rule of thumb is we try to get something factor of 10, factor of 3 at least, better than this.
To what extent do you think you've pushed the state of the art in terms of engineering anywhere? To what extent are you, is there engineering this standard in any other endeavour of precision engineering?
Gravitational waves.
Outside astronomy.
Oh, outside astronomy. Well, some of things like the fusion research, I think, is an area where we've got similar types of challenges, optical ones as well. Things like laser containment of laser fusion.
Yeah,
that's got some sort of challenges.
Some sort of optics, I guess.
Yes.
It's called field spectroscopy, etc.
Yes. But I think in general we aren't sort of pushing to say we aren't usually.
Okay, no. Thanks very much. So now we go to the opposite extreme. We've imaging things at solar sizes, as in the universe, to super resolution multi-dimensional microscopy for cellular imaging. This is presented by Paul Dalgarno and Heriott. It's part of collaboration between Heriott University and Edinburgh, so that's the field of super resolution microscopy.
Okay. Yeah, right. In my entire career, I don't think I've ever had to follow 2 talks quite as epic as that. So, right. Hold on. We've gone from the very big to the extremely small. I'm going to talk about microscopy, but you're going to find that there's an awful lot of links actually, coincidentally. So, most of us know about microscopy. It's one of the oldest of the modern sciences, from back in the 17th century when people like Galileo and other people like that developed the first, what we consider now Galilean type microscopes, and did this wonderful. Science was better back then. You looked down these microscopes, you used candlelight to illuminate the sample, and you sketched what you saw. And the publication of Microscopy back then changed microscopy and science forever, because Robert Hooke showed the world the very small. And then microscopy has evolved significantly to these state-of-the-art, hugely complicated microscopes that you can buy today that look completely worlds away from where it began a few hundred years ago. And in the middle, you've got these beautiful looking instruments. And science by then became a little bit more artistic. You drew what you saw, but you added your own flair. So if you look at any material from then, the Microsoft world looks a lot scarier than it really is, because they wanted it to look like a show. And then these new microscopes here can now do amazing things. We can look inside the cells that make us work. We can use fluorescence, we can do everything like that, to try and understand life at the fundamental limit. However, that brand new scientific microscopes that you can buy this year is exactly the same as the one that Robert Hooke used in micrography, exactly the same. There are fancy detectors, there are fancy lasers, there are fancy stages, and there's computers, but at its heart, a microscope is 2 lenses depth in an eyepiece. You pair them together, and they create your magnified image. At its core, all these instruments are identical. And that's important because it gives us fundamental restrictions on what we can do. So way back when, this Silverton fella A demonstrated something that we now know as the diffraction limit. Light is a wave, as we all understand it, and as you put it into an optical system, like a microscope, it diffracts. So as it goes through the objective and it diffracts, what it means is that if you're imaging an infinitesimally small point, if you're imaging a point source, what you see on your camera is not that point source, a nanometer-sized point. What you see is an extended object. It extends in X and Y, and it extends horrendously in Z, and called the point spread function. That's because of diffraction. What that means is that, and Abe demonstrated this in 1873, and about 10, 15 years after that, you could experimentally reach the diffraction limit. And then for over 100 years, that limited microscopy. Doesn't matter how sophisticated your technology is, you can't beat the diffraction limit. So because of that, if you've got 2 objects that are very close together, that are point sources, you can't resolve them, so your microscopy is limited to a few hundred nanometers. That's a problem. If we want to look inside cells, I work with a lot of biology colleagues who want to do that, you can take a beautiful image of a cell, you can make it fluorescent, you can make it shiny, you can see what's inside it. But this is a neuron, this is a real neuron, that's what's trying to trigger our brains right now. And as we want to look inside it, if we look closer, we can magnify it, but we just see a blurry mess. We can't resolve the individual features inside the cell, and that's what we're interested in. Those individual features, those proteins, those cellular machines, are about the nanometer in size, roughly, the small ones, the interesting ones. And we would love to be able to tell you where they are, what they're doing, and how they're playing with each other. But we can't because a microscope can't give us that. So this was a huge problem until about 15 years ago, when a selection of different groups in the world, it was a big debate in microscopy today, but I won't go into that, did something remarkable. And they understood that. They understand that. This is optics that we understand. And they said, well, I know what the diffraction line comes from, and I know what it looks like. So what I can do is this. If I've got a single point source going through my microscope, and I image that point cloud function, all I need to tell you is where the middle of it is. So it's localization microscopy. If I can tell you where the middle of that point cloud function is, that is where my particle is. This is known, this has been known for a long time, about the dimension of localization. Astronomy not talk. But applying it to microscopy is a little trickier. So if I've got two objects that are extremely close together, and I want to tell them apart, I can't have them both turn on at the same time, because I will never be able to distinguish that. So what happened in about 10 years ago, and a Nobel Prize was awarded for this 2 years ago, was the development of single molecule localization microscopy. And what it does is it works a bit like this. Here's an image of a cell. This is a real cell. It looks like a Christmas tree. All your cells look like Christmas trees in December. What happens is we mutate and we get the festive feeling. So this is our Christmas tree cell taken in a normal microscope, and everything's a little bit blurry. What we've done is we've labeled part of the cell, be fluorescent. We're interested in what that label is. The biology doesn't matter. But I can't see any details because of diffraction. What single molecule localization microscopy does is you modify the way that the cell is emitting light, and so that all of the molecules are flashing on and off randomly. They flash, they flash, they flash. You take a movie of that to look like this. What you do is for each movie, you then take that image out, you find out where the spots are, you localize each spot, you record that information, and you repeat the process. You need millions and millions of data sets to do that. It's quite experimentally challenging, but when you do it, you can get something that looks like this. Same cell, imaged in super resolution. Our resolution here is now about 20 nanometers. 10 times better than the diffraction. What limits your resolution, what limits your accuracy and precision in this experiment is how many photons you can get. The more photons you can get, the better your signal to noise, the better your localization becomes. This is a completely different image from this, and it tells you a completely different thing, hence the Nobel Prize for it. So microscopy's come a long way in a short time. It was largely not stable, but it hadn't progressed a lot in 100 years, and then it went, oh, and cellular microscopy changed significantly. But there's still a number of challenges. There's other, this is called super resolution microscopy, if you're not familiar with it. There are other ways to do super resolution, a bit more complicated. I can chat to you about them if you want later in the day. But microscopy has another issue. So here is a microscope that I built in my lab. This is a demonstration. You can take it with the train. And then all it's doing is imaging those three transistors, resistors, and they're in depth. You see, if you've got a cell, your cells are three-dimensional. So they're small, but they exist in all dimensions. If I want to look at the proteins inside them, I would ideally want to look at that in all dimensions. So if I take this little demo microscope and I image these here on a standard camera, then what I see is this. One of them is sharply in focus, but anything above or below it, in front or behind it in this example, is blurry. Microscopes, despite all of their advanced things, microscopes, one of the underpinning technologies in science, are inherently two-dimensional imaging systems. If you want to access the three dimensions of the world, you can do it one of two ways. The first one is you take a stack, you take an image here, 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 here. You combine it together, and you can create a 3D representation of your object. Trouble is, that's slow, it takes time. But everything inside your cells are active. Cells are unbelievably active. Everything is moving, so your cells have billions of these proteins, all of which are moving and interacting in an exceptionally complicated way. Probably one of the most complicated systems we as possibly think about. And we're trying to work out how it behaves. Everything is moving, everything's doing 3D. So I can localize these particles. This is an example of something called pages on material. And they're moving around, and if they move in X and Y, that's fine. I can tell you where they are with ultra high precision. The second they move up or down, we lose information. So what we can do is we can take a stack, but it takes too long. So if I take a stack, I can't track where it's moving, or I can record a movie in time, but then I can't access the other dimensions. A microscope's three-dimensional, x, y, and z, or x, y, time. So one of the projects that I'm involved in is trying to resolve that, combining these two elements. Can we get ultra-high resolution microscopy in all spatial dimensions? There are a few approaches to do it of varying complexity. The simplest one is to simply split your image up. Split the object, the image from your microscope, up into 2 or 4 or more than that. Separate it in a simple optical path, put a different focusing power in each path, put it onto one camera, and you can get 2 images in the top diagram from 2 different depths inside your cell. Okay, the 2 image planes doesn't count this very much. We probably want more than that. If you want to do something like 4, this group earlier this year published a nice paper where they did it. This is a commercial system that they modified by putting on lenses to get 4. That works quite well. Unfortunately, if you ever have to change the parameter space, you have to completely rewrite the system, and that's difficult. Because one thing we have to consider is that what we're talking about here is microscopy applied to molecular biology. The biologists who I work with, who I collaborate with, this is hugely interdisciplinary work, and they're spending all of their time and effort doing massively complicated molecular chemistry. They don't want a massively complicated microscope to go and use. In the past 20 years, there have been many physics and optical groups designed fantastic microscopes that can do amazing things, but they're completely impractical. The only people that can use them are the people that have designed them. And for that reason, they haven't been used universally throughout the life sciences. There's a limited application to this. We need a simple solution to this so that the people that are trying to use it, the biologists, can actually put the effort into doing the biology. And so true interdisciplinary needs to bridge those boundaries very well. So these techniques are somewhat specific. So what we've been working on at Heriott is a different approach. And actually, it's hugely linked to the previous talk. We use diffraction gratings because diffraction gratings are simple. A diffraction grating, most people know what diffraction grating is. You have repeating black-white, in this case it's a phase grating, but it doesn't matter. And pattern, if you send an image through a diffraction grating, it splits it into each order. If you design your grating in a certain way, you get most of our energy in the first 3 orders. You do that in the top diagram there, and you basically split your image into 3. Right? That's just a beam splitter of sorts. If I then put a second grating behind that in an orthogonal way, I can then split that image into 9. So I can get 9 identical images on my camera. Who cares? But if you change that grating, take something called a Fresnel zone plate, which is like a circular diffraction grating or concentric gratings. It's what they used to be in the old overhead projectors or in lighthouse lenses. If I cut part of that off, create an off-axis Fresnel zone plate, I create a diffraction grating where the lines are curved. That curvature has a very big effect. Because of that, the way that curvature interacts with the optical system, I'm not going to go into the detail, it introduces a focusing power in the non-zero order. What does that mean? If I shine light through this grating, it splits the light into 3, but in the positive order, there's a focusing element, and in the negative order, which is a refocusing element. This technology was designed originally by Colin and himself, to do the wavefront sensing in astronomy that you heard about in the previous talk, or a version of it. This is astronomical technology. But what we've done is we've changed it and we scaled it down to apply to microscopy. If you pair that up with a lens in the right way and put it on your microscope, you can now image your different depth inside your sample. And that's what we're trying to do in order to get ultra-high localization precision in all spatial dimensions. The benefit of this is it's a remarkably simple optical system. Very short unit that's about this big, or depending on how you're building it, it's this big. You can change the gratings very easily, so you can change the distance between the planes. And there's a couple of issues with it, I'll mention some of them. And then you can image, in this case, either 9 or 3 planes. The top one's the beads moving randomly under Brownian motion. This doesn't work anymore. The bottom one is vascular movement inside cells taken at the Beats Institute here in Glasgow. And the whole point about this is you can pick it up and carry it around. I would have taken it with me today to show you, but immediately after this, my institute has its Christmas dinner night. I don't want to take it with me. I don't trust any of them with this, alcohol and biologists. Yeah. So it's about this big, and that's important because I can take it and plug it onto any microscope there is. That matters. So now we've got the system and we're accessing 9 planes. 9 planes doesn't seem like much. But actually, it's more than enough. 3 planes would do. Because now we want to talk about localization. But a simple optical system is something that's strongly how do we do it? I've got a microscope with 1 plane, 1 imaging plane, standard microscope. And I've got my object in focus in that plane. Maybe a nice little sharp point, this sharp point's red one. If I move it, if I defocus it, I'm moving up and down that defocused net. So I will see one of those images as I defocus it. And I want to know how that relates to how defocused that spot is, how much it's moved in Z. It turns out, many people think, well, look, I can see that shape there. I could probably model it. I could flip a function to it, and that will tell me what I need to know. The truth is you can't. The optical system is so complicated. There's so much aberrations. It's so dependent on tiny details. You can't do that to any degree of high precision. People have tried. It's not being not in the sort of a highly adaptive environment of the cell. It becomes difficult. So the major problem is that if I move this, it can be hard to tell you even what side of focus you're on, not in this example. So what we do is we use something else from astronomy called image sharpness, which is ridiculously simple. You draw a box around your point that you're interested in, you square all the intensities, you sum them together, and you do some normalization. And as a function of defocus, you get a graph of it. So this is where it's in focus, and as it falls off, the sharpness value collapses. On its own, that's not very helpful, but if I've got more than 1 plane, then this is what happens. If I've got a particle here, and it moves into this plane, it gets blurrier in here, it gets in focus in here. So the sharpness falls here, then it rises here, and this one can be used as another reference. By combining this information, I can tell you exactly where the particle is. I don't need to image it in focus at any point. If it sits here, I can say what is its sharpness value in this plane, this plane, and this plane, and I can refer to some reference calibration curve and tell you its position axially. That's what we're trying to do. And it works quite well. But just by multiplying how many image planes we have and extrapolating information between them, we get a form of axial localization to pair with the lateral localization. There is a huge problem with it, and that is gratings are inherently chromatic. You shine white light in a grating, you get a rainbow. It's pretty, it's a big problem for us. We're dealing with fluorescence. Fluorophores have a modestly broad bandwidth of emission. And the key point to all of this, the key point to microscopy is every photon counts. You never want to throw away the point of information, because that's just going to hurt how much information you gather from the system. We're dealing with very, very weak photon limits here. And 100, 200 photons being collected isn't uncommon. We don't want to have to get rid of it. We want to collect all that bandwidth, but if you do that in another systems, it looks pretty, but it's a pain in the ass. You get this chromatic blur. And this has caused the problem of grating-based imaging systems for quite some time. Because if you look at a cell, instead of this, you get this. You lose all the information that we're after, not only axially, but laterally as well. And there's a simple solution. We could aggressively filter the light, but then we throw away all the light. And that doesn't really work. There are some optical solutions, again, with its origins in astronomy. And we've explored several of them, and they do work, but they come with frustrating compromises. They're hugely expensive, they're hugely complicated, they're very large systems, which are difficult to align, but they're also not very adaptable. So if you change your wavelength, if you change your fluorophore, if you change your cell, you have to redesign your entire optical system, and that becomes quite an issue. So this held us back quite a while, until we then realized that actually there's a simpler solution. We know what the grating is, we know what causes this effect, we know our optics, so we can just deconvolve the problem. Just use a relatively simple deconvolution, and it works quite nicely. There's a little bit of detail in here that I don't need to go into, but this is the ideal image that we get from the reference to the order. This is what happens when it goes through the grating, and we can deconvolve it back to obtain a lot more information. Now, it looks like there's a horrendous noise floor on that, but it's just the way that it's being shown on the screen. It's not nearly as bad as it looks. And by doing that deconvolution, which is relatively straightforward, we can get all the information back. Remember, all we're trying to do is localize it. This is an important point. I don't need to recover all the information in these images. I just need to recover enough for me to localize it accurately. They're slightly different problems, and that's more than enough to do that. So that's what we've been working on for the last wee while. You then need to reference your data back in the sharpness data reference. We use some statistics, maximum likelihood statistics. It gets a little bit detailed, but it's nothing new here. This is all applied from other techniques. And what we've done to get that is we've put it all together into a plugin for package an open source software plugin that does all this for you. So the whole point of the project, this has been funded for many, many years. It started with SDFC funding and it's evolved through the GBSRC funding. And with the last GBSRC grant saying, right, you know what you're doing now, write a program and develop a system that any biologist. We're just finishing that off now. So you don't need to know any of the details that I've gone through to do it. And it all comes together to something like this. Here's an example from a real cell. So this is a cell undergoing extreme autophagy. The cell is literally eating itself to try and survive. It didn't survive. We're tracking all of the autophagosomes, the particles inside the cell that are responsible for this process. We're trying to work out how those particles interact with themselves, how the process works, and autophagy goes wrong with diseases. And here's an example of a particle moving around in X, Y, and Z. We can track it in X and Y with high precision, but as it now moves in Z, we're beginning to be able to track it. What causes the limitations? Well, it all comes down to how many photons and if your background is stable. And in real cells, those are very difficult problems. So this is not yet super resolution in Z, but the principle is there. So if we had a cleaner system with a brighter spots, we would be able to do that. And the idea, in an idealized test case, we can get axial resolution down to 5 nanometers instead of 500. So 100 times better than the diffraction limit. But that is an ideal case due to the test samples. And that's where we're at just now. So I realize it's very late, but that's been done, nice and short. I'm just going to very briefly thank people who have done it. Eric Keating now works in Manchester. He wrote all the code, and Becky did all of the cell work. And this came from Alan L. who just briefly mentioned the previous talk. Where the next generation of this project is now moving to apply the adaptive optic corrections just heard about in collaboration with the ATC in Edinburgh to try and improve the imaging quality further. Okay, thank you very much.
Thank you. Do you have some questions for Paul, please? What sort of depth of field is each one of your 9
well,
achieving?
That's a good question, and the benefit of using the grade system is we tune it. So we just swap grades to change that. So the work that I showed you, the previous slide was 600 nanometers, but they're quite flat cells. Quite contrast. But the whole project was designed for the golden number in biologists is 10 micron cells. So most mammalian cells are 10 microns. Not all of them. You have some cells that start here and end in food, but they're weird, so we don't talk about them. So 10 microns, and we can put 1 micron. And that's enough to do the extrapolation. Too far apart, you can't extrapolate. Too close together, you don't get the depth.
So I guess as these go out of focus, you clearly signal to noise ratio to grades.
Yes.
Is that what limits your ability to localize them in Z?
Yeah, it's not as simple as just aggregation because you're using information from multiple planes, so you get something back. But ultimately, it's overlapping the focus point spread function. If they overlap, it's really hard to detect, especially if they're noisy. And it's just how many photons you have in your signal. It all comes down to there's a 1/2 factor for how many photons you have. You just want as many as possible. And it's a bigger problem when you defocus it because you're spreading it out. Your noise affects it.
So you can do these calculations on signal to noise ratio, you get some favorable bounds or something like that. Then you can do the measurements. How close does your measurement come to your prediction?
They map reasonably well, but actually one of the bigger problems for us is an uneven background. So when you're trying to do it over the spatially extended cell, as you've got the uneven background, it messes up how we're comparing the calibration data. So unfortunately, cells don't deal with each other too. We repeatedly ask them and they repeatedly refuse. So it is really pushing the limits of what we can do with the atomic signature. And on top of all this, we've got various other projects that we're trying to gather more information from that atomic signature as well to try and help.
So I know this work started off with Ministry of Defence funding.
It did.
I think you've been to every research council probably. Would you talk to people still about these problems, for example, in astronomy?
Well, yeah, we've got. I've just got a CDT student started a few months ago with Noah from the ABC, applying adaptive optics to it, because a lot of the mathematics that we apply and a lot of the optical techniques came from astronomy. We've got a strong interaction with the SDFC, one of the Napkin labs down in Oxford. And actually, most of the sort of stuff that I've been talking about here in the advances in the last 15 years have come from physics and chemistry development detached from the life sciences. So that's why this has been funded so well from the SDFC and various bodies from that.
We have time for one more question.
I was thinking, with a DMT class,
yes, you don't quite have the resolution that we need for that. So due to the curvature of the very extremities of these, especially for the large plane spacings, you need a really high resolution in your grading system. It would work, but that's much more applicable to the sort of astronomy applications where these planes have different ways. So we did look into that in some detail, but it doesn't quite give you what so it's just good old-fashioned grading optics.
Any more questions? Well, I'd like to thank all of this morning's speakers as well as Paul. I've really enjoyed this morning, so we've drifted on a little bit, but I think that's absolutely fine. I suggest we reconvene at 11 o'clock. There's tea and coffee just outside here.
I did actually.